All right, today we go right back to transformations, transformation of trigonometric functions. And if you're really good at transformations, then a lot of this will seem pretty straightforward. But there are a couple little quirks when you go to do transformations on trigonometric functions. So a bunch of this will be a review, and then you really want to tune in for the examples because the examples have a couple of little things that you got to add on to your thinking. So you've already seen most of the material that we're about to cover in this lesson. The major difference here is that we'll focus on the use of radian measure when transforming the graphs of y equals sine x and cos x. Recall the following transformations. A negative out front of the function will reflect the function in the x-axis. A negative inside the function will reflect it in the y-axis. A number out front of the function will vertically stretch it if the number is greater than 1, and it will vertically compress it if the number is less than 1. And finally, a number inside the brackets, a multiple, will horizontally compress it by a factor 1 over k if k is greater than 1, but if k is between 0 and 1, like if it's a fraction, it'll actually stretch it. So again, what happens inside the brackets always seems to be the opposite of what you would think, like a multiple of 3 out front multiplies things by 3, but a multiple of 3 inside would divide things by 3. You'll see some examples of that. Let's consider a few examples in which the transformations are applied to the functions y equals sine x and cos x. Well, just a quick review of last section before we start about what you should know about y equals sine x and y equals cos x. So just a little sketch of each one from what you should have got from your investigation. For y equals sine x, what you should have discovered was that you get a function that's like this, and I'll just extend it a little bit and put an arrow at the end to say this keeps going in this pattern like this. Its high point is 1, its low point is negative 1, and so what we say is its amplitude equals 1. It goes up 1 from center and it goes down 1 from center, so it's got an amplitude of 1. Now, the other big feature is that because this is a periodic function that repeats, it's always good to know how long does it take to repeat, and the answer is 2 pi. So we call it the period. How long it takes to repeat is 2 pi. Every 2 pi we get a repeat of this thing. Some other interesting features, though, is that means the halfway point here is pi, this high point here is at pi over 2, and this low point here is at 3 pi over 2. Those are good points to just know on the sine graph because they're good reference points to use. When we were doing transformations on all kinds of other functions, we had reference points that we used, and we'll often use these reference points of the sine graph when we're doing transformations. Y equals cos x, very, very similar. One little change. Again, 1 and negative 1 are the limits there on the range, and then it does the same thing as it goes up and down like this periodically, and it does it in 2 pi. So these key points are at these same locations. The only difference is where it starts. Cosine starts at 1, whereas sine starts at 0, and so still amplitude is 1, and the period is 2 pi. Well, the period's 2 pi and the amplitude's 1 before we do any transformations, and that's the big thing that's going to change here is when we do these transformations, things are going to change up. I also want to mention that sine and cosine are the basics of math of any kind of wave, whether it's a water wave or a sound wave or a light wave, electron waves, all of these things, sine and cosine provide the basis for doing all that kind of mathematics. So the importance here is not to be overstated. Like it's huge, the applications that come from sine and cosine. And before we move on, we should address the following questions. How do you know if a question's in radians or degrees? And you just look at the type of angle measurement used in the question. If the question is given in degrees, then use degrees in your answer. If the question is given in radians, then answer in radians. This is important, though. If the type of angle measurement is not given, we mean radians. Radians is the fundamental measure of angles, so it's the one we use when we don't see anything. Now, this example here, I don't intend that this first example is something that you should be able to do at this point. The first few examples, like examples 1, to, even after some more notes, example 3 was in there. The first 3 examples, I just want to give you a feel for what these transformations do to these functions. So don't think that at this point I think I've explained enough to be able to do the things you're seeing on the screen there. It's sort of like a tour. Let's take a look at how these things play out. And then starting at example 4, I'll really start giving a set of steps for how you should approach these questions. So example 1 says, sketch one cycle of the graph y equals 4 cos x and y equals sine of 3 x starting at 0. State the domain and range of each cycle. Well, the only thing that changes in this 4 cos x is this multiplier of 4 out here that we see. That's the only thing that's different than the cos x that we saw up here. So it's all we're going to be trying to draw is this graph of cos x that we saw up here, but it's going to be vertically stretched by factor 4. Well, the word we're using for how much up and down it goes was the amplitude. And so we're drawing the exact same graph I just drew, but instead of going from 1 to -1, it goes from 4 to -4. So the vertical stretch is fairly easy to handle with sine and cos, because all it does is takes the amplitude and multiplies it by that factor. And it just changes the scale choice you make here. In fact, a lot of the battle here in graphing trig functions is about scale, is about getting the right scale. And so you see in the picture there, they used a scale that went up to 4 and -4, and that allowed the graph to go from 4 to -4. Now the domain and range of the cycle that we did there, that cycle went from 0 to 2 pi. Now notice they said the domain range of the cycle. So that what they mean is one loop of this thing, what you see in red there. Sometimes they might ask for domain and range of a cycle or maybe the whole function. But of one cycle, it goes from 0 to 2 pi and the range goes from -4 to 4. Notice the period was unaffected by having a vertical stretch factor. The next example though is y equals sine 3x. And this one's a little bit difficult to follow exactly what's happening with the period. So I'm going to give you a formula in a minute to really handle the thinking here. So try to follow the thinking the first time, and then at the end I'll give you a formula to try and help. The graph of y equals sine of 3x is the graph of y equals sine x, but it's been compressed by a factor of 1/3. So instead of having a period of 2 pi, the period's been decreased by a factor of 3, which becomes 2 pi over 3. If you follow that perfectly, you might not need my little formula, but the formula just provides a nice, easy way to do all that thinking. It still has amplitude 1, but now that we have to look at the period being 2 pi over 3 is, let me add some scale here to this thing. They've used a scale of pi over 3s, which was a great choice here to use. So again, I say, the choice of scale will be sort of fundamental in making it nice and easy to graph these things, because when they used a scale of 2 pi over 3, that made them able to find the other points, or a scale of pi over 3, that made finding the period of 2 pi over 3 easy to do. If they had used a different scale than that, things might have been a little bit more troublesome. Okay, so my formula that I suggest for this section is when you want to find the period, take the 2 pi, which is the normal period, and divide it by the k value. And that's what I'm going to call this number right in the brackets here. Whatever that number is, whatever that horizontal stretch or compression factor is, just divide by it, and you'll get your new period that you can use. And that'll really help you to decide on a scale. I'm not giving the steps just yet. I will give steps about example 4. But for now, I just want to say that's something I'm going to use later on. And then the range of this cycle was -1 to 1, because this time there was no multiplier out front, so there was nothing that affected the amplitude, so the amplitude stayed at 1. A couple of comments in the last example. Notice that vertical stretches and compression affect the amplitude, whereas horizontal stretches and compression affect the period. When compressing the graphs of sine and cosine, notice the key points that were used for reference. So these key points that I mentioned up on the previous graph, and you can see here, and I'm not using a very good color there. Let me switch to green so you can see what I'm up to there. These key points on there are very handy, and the order I graph them in is I start with the first and the last point, then the middle, and then the middle of those middles. And if that's not clear exactly what I'm talking about, oh, just wait. You'll see. Like I say, when we get to example 4, I'll really go through the steps of how to handle this, all this stuff together. Well, here's one that does both at the same time. It says sketch the graph of y equals 3 cos 2x. And for me, starting to move towards those steps, right at the start, then I would write, okay, the amplitude of this thing is going to be 3 because there's a multiplier out front of 3, and my period's going to be 2 pi divided by that k value. That's the name I'm giving this thing. I'm calling it the k value. sort of comes from physics later, I got to tell you. We talk about K waves, and so we often call that number the K value. So I get a period of pi. And just making those two little notes before I even start really helps with deciding on the scale and how you're going to draw this thing. And you see, they've used that scale nicely here. They went 3 to -3 on the graph, and when they went to do the scale, they see they used pi right there on the scale because they knew that was the period. So then all I got to do is draw something that goes up to 3 and down to -3 and repeats every pi. And you see they've drawn, there's one cycle there, and it takes exactly pi to do one cycle. Now, this question didn't say sketch one cycle, it said sketch the graph, and that's why you see it continue on from there with arrows on the end of it to indicate this thing is periodic in nature. It just keeps going on in both directions. The other thing is they said graph it over the domain -pi to pi. My screen jumped there. And so they want a graph that goes all the way from -pi up to +pi. They went a little farther than that, and we're not going to bust you too much on these if you don't get the domain exactly right that you're doing there. But really make an attempt that when they ask for this much of the domain, get at least that much. They want to see that much of the picture. The only way this can be turned around is they give you the graph and they want you to determine the equation. And I say again, making a couple little notes to yourself down on the side before you even start to try to answer the question about amplitude and period can really help in answering the question. For instance, I can see in this graph it goes up to 5 and down to -5, so its amplitude is 5. So when I go to build the equation, that's what goes right there as the vertical stretch. And the period, how long does it take to do a repeat? Well, I'm going to trace it out here and say, okay, it went all the way to 4 pi is the period. And then it's a little confusing exactly what K value to use in there, but my formula helps you out. This period where you go, the period equals 2 pi over K. I'm going to rearrange that formula to get K is 2 pi over the period. The period here was 4 pi, and that's how they get the 1/2 there. So the formula is a really nice way to handle that. If you're thinking, well, I can think that through. The original period was 2 pi. Now it's 4 pi. It's been doubled. That means it's been horizontally stretched, factor 2, so I need a 1/2 in the brackets. Yes, that all works. That's perfectly fine. But the formula does all that thinking for you. So that's a very nice formula for dealing with periods and K values. Okay, so that it has both ways now. I've covered amplitude and period both ways, from the equation to the graph and from the graph to the equation. There's a couple more transformations we have to deal with. When there's a number outside the brackets that's being added or subtracted, adding means go up and subtracting means go down. And when there's a number inside the brackets, adding means go left and subtracting means go right, which is sort of strange that adding would be left, but everything in the brackets sort of operates the opposite to what we would expect. And that number in the bracket has a special name in physics, and we start to use it in math here a little bit. That number, that horizontal translation is often called the phase shift. And when applying a combination of transformations to a graph of a function, remember it is best to perform the reflections and stretches before performing the translation. Some of you might have learned how to do this with a table of values before, and you always had to do stretches and compressions first. And there's actually a simple reason why that's true, is it just follows BEDMAS. You do division and multiplication before you do addition and subtraction. So that's why you do those things first. Okay, here we go. If you got an extra gear to your brain, now's the time to turn on, because now I'm going to go through all the steps of graphing something with all of the different features in there, and I'm just going to do different situations. So 4, 5, 6, and 7, just all sorts of different situations. Ooh, that's been moved down a little bit. So I'm just going to talk a little bit why I fixed that. And so that you see many different examples that you can refer back to, some different combinations of phase shifts and stretches and compressions and all those things in each one. But the same set of steps each time. So I'm hoping I give you a nice recipe for how to deal with all this stuff at once. Okay. They give you a equation, and they want you to graph it. The first thing I do is I write down, okay, what's the amplitude? And here the amplitude is 2. That's that number out front. It's the vertical stretch. Now I know this graph has got to go up to from +2 down to -2. Excuse me. Then period. I use my fancy formula. 2 pi divided by the K value. Well, in this question, there was no vertical stretch, or sorry, horizontal stretch there. There was no K value, so the K value is 1. So nothing happens to the period here. the period will be 2 pi. Every cycle will repeat in 2 pi. Next, we check and see if there's a phase shift, which you can call horizontal translation if you want. That's no problem. I'm going to call it phase shift in preparation for physics type stuff. And phase shift, there's none here. There's nothing inside the brackets as far as a phase shift. But there is a vertical translation. And the vertical translation is up 3. I get that from that plus 3 at the end of the function there. Now, the other thing I'm going to add to this is thinking about what scale to use. And I'll put scale with a question mark there because we just have to, there'll be a wise choice for scale that might have to be changed if there's something else going on, if there's a phase shift. Here there's no phase shift, so that me putting a question mark after this scale thing might not make a whole lot of sense. But in later questions it will. So scale question mark. I say for a scale, we use period over 4. That's going to be a great scale. And the reason I say over 4 is way back to these key points that I mentioned way up here, is that there's 4 sections, 1, 2, 3, 4 to this graph. And with 4 sections in the period, a scale of a period over 4 will nicely come up with the points I'm looking for. You'll see what I mean in just a second. Here the period's 2 pi over 4, or it was 2 pi. So 2 pi over 4, it's suggesting a scale of pi over 2. And just in the interest of making this picture big, what I'm going to do is use a scale here of pi over 2, but every second squared, just to make the picture big so you can see it. Pi over 2, every grid line would be a great choice as well. Now, follow my thinking here. If the scale's pi over 2, what I'm doing is counting by pi over 2s. So pi over 2, then I get 2 pi over 2, which I'm going to write down here. As you get better at them, maybe you don't need to write them down there, but 2 over pi over 2 is just pi. The next one will be 3 pi over 2, because I'm counting by pi over 2s. And the next one will be 4 pi over 2, which reduces down to 2 pi. For scale this way, I'm just going to go 1, 2, 3, 4, 5, 6, 7, -1, -2, -3, -4, -5, just something like that. That'll handle both that amplitude of 2 and the fact that I've got to vertically translate things up 3. Now, me personally, you can do it all in one step. I don't. I first draw a bit of a drawing of a graph that has the right amplitude and period. Here's what I mean by that. And I'm going to go to another color, sort of a light orange here, that you can, hopefully when it's done, won't be the major feature of things. The graph of sine starts at its top. I know when I say graph of sine, people immediately say, oh, it starts at 1, because that's what graph of sine really does. But in the case of transformation, see, if you look up here, the graph of sine, the graph of sine starts at 0. And so in this one, I'm starting sine off at 0, and that amplitude of 2 doesn't affect that. So I'm going to draw a point on there. Now the next key point is at this pi over 2. And if you're not buying into that, just watch what happens. This choice of period divided by 4 is really going to pay off here. At pi over 2 then, because it goes to amplitude 2, it goes up to 2, then it comes back down to 0, then down to -2, then back to 0. That's the pattern of those key points from sine. It starts in the middle, goes to its top, which in this case is 2 because of amplitude 2, goes back to the middle, down to the bottom, which is here is -2, and back to the middle. That's the pattern of key points for sine. Now, a couple of things. Notice that by using period over 4 as the scale, and those being my key points, I automatically created a graph that had period 2 pi. That worked very, very well with choosing a period divided by 4 as my scale, because what happened was when I did 4 points, I ended up with exactly the right width of graph for period 2 pi. Now, here's what I do. You might be right with me to go, yes, you've now got the right period and you got the right amplitude, but you got to move these all up 3. So that's why I don't draw a curve through these points. I just use them as reference. And if you're drawing them on your graph, draw them sort of light so you can just barely see them, just enough to use them. Because then my final graph, which I'm going to do in the brightest red I can come up with here so you can really see it, I'm going to take all those points and move them up 3 and make it so I can ignore those orange points. Up 3 gives me this point. Up 3 gives me this point. Up 3 gives me this point. Up 3 gives me 1, 2, this point. And then up 3 gives me this point. And now I've got my points that I can draw a nice smooth curve through. And I'm going to label that curve. It says state the domain and range of the cycle. So it says sketch one cycle. That's what I've done here. So I'm not putting the arrows on or anything like that. I'm just doing sketching of one cycle. I'm going to label that y equals 2 sine x plus 3. And it said state the domain and range of the cycle. I've got to find some space here. Domain, x element of reals, 0 to 2 pi. And range, 1 to 5. All right, so hopefully you now see a set of steps, and I'm going to use that set of steps again and again and again now for the next few examples. So if you're like, okay, I sort of get all the steps, but not really, that's okay. I'm going to just keep repeating them here and just keep doing those over and over again. This one here, example 5 now. Switch back to that green, which I like. It says state the amplitude, period, phase shift, and equation of the axis. I haven't talked about equation of the axis yet, but I will by the end of this example. So, amplitude is just that vertical stretch that's off the front there. Amplitude here is 0.5. Period. There is no K value here. There's no horizontal stretch or compression here. So the period's 2 pi. It also said, talk about the phase shift. And this phase shift is what we called horizontal translation before. And it's pi over 2 left this time because it's plus. There's no vertical translation. It didn't ask for it, and that's because there wasn't one here. There's no vertical translation here. Now, it asks me to graph this thing. And so these two other pieces that I'm going to do here, same as I did up here. So I'm going to think through a scale, a good scale. And again, if this question mark confused you, I get to talk about that in this example, whether this scale is a good choice. The scale that I will choose every time is I'm going to try period divided by 4. That'll make my key points play out nicely, and it's suggesting a scale of pi over 2 as well. Here's the question mark part. Check to make sure that scale works well with the phase shift. Because if it doesn't work well with the phase shift, it's going to be tough to do the phase shift afterwards. Now, this one does work really well. It's going to have key points of pi over 2, and I'm going to phase shift pi over 2. That's going to work very, very well. But if that doesn't work very well, the actual scale that you're going to use will have a common denominator between these two things. That doesn't come up too often, actually. But there's a couple of homework questions where you may have to look at and go, oh, that phase shift doesn't work well with my scale. And what you'd do is you'd find a common denominator between these things. Like if that was pi over 3 and pi over 4, which doesn't work well together, use a scale pi over 12, and things will fall together nicely. So it said sketch one cycle again. I'm going to again do that thing where I skip a square just to make this thing nice and big. I'm going to go pi over 2, pi, 3 pi over 2, 2 pi. Just to make it big so you can see it really good here. And then for a scale, I'm only going to go up to 0.5 and negative 0.5 here because the amplitude is only 0.5. So this time I'm drawing a cosine graph which starts at its top. And by top, what I mean by that is the top of the amplitude. The top of the amplitude here is 0.5. So here's a graph that just has the amplitude and the period. And again, I've chose that light orangey yellow color so I can draw these points and make it so that they sort of aren't the main feature of this graph by the time I'm done. So start at the top, middle, bottom, middle, top. That's the pattern of the points for cosine, of those key points. And I'm not going to draw a curve through it. You can if you want, but I don't draw a curve through it because I know those aren't the right points for my complete graph. I've got to take all of those points and go pi over 2 left. Now, what is pi over 2 on this graph? It's 2 squares. So I've got to move everything left 2 squares. Notice, because I chose a scale that works well with the phase shift, it's exactly 2 squares. It's not some weird amount. So I move this one 2 to the left, to the left, to the left, to the left, to the left. And so it says sketch one cycle starting at x equals 0. So I got to start here, there, there, but that doesn't complete my whole cycle. So I'm going to add the next point in the pattern there. There's my one cycle of the graph starting at x equals 0. And there's my graph y equals state the domain for the entire function. Oh, so the domain for the entire function this time would be x element of reals. They didn't ask for just one cycle there. And then range, this goes from negative 0.5 to 0.5. Okay, so very similar steps at both those times. I state the amplitude and period, phase shift, and vertical translation. I do a little thinking about the scale. I draw a graph that has only the amplitude and period correct, and then I do my phase shifts and vertical translations afterwards. Ooh, this example, a little more torque to it. It's got everything in there. Let me go through the steps again. Hopefully the steps are becoming a little more predictable here. I'm going to look for the amplitude. It's that number out front, which is a 4, not negative 4. This is the first example that's had that negative out there, and I got to talk about that in a second, and I will. I'm going to put that right there. Vertical reflection. There's a time for it. There's a time to do that, and I'll show you exactly where that is. Period, 2 pi over the k value. I'm calling this k value, that number, that horizontal compression in the brackets there. It happens to be a 2. So I've got a period of pi this time. Phase shift is pi over 2 again, but this time it's pi over 2 to the right. There's no vertical translation, so you don't have to write vertical translation none, like I'm doing here, when there isn't one, but I do anyways. Okay, so those steps are always going to be your first step when you're graphing these things. You're going to state the amplitude, state the period, state the phase shift, state the vertical translation. Then a decision on scale, and I'm suggesting a great scale will be the period divided by 4. And here the period was pi and divided by 4. But just do a double check that that works well with the phase shift, and it does, because pi over 4 and another pi over 4 is pi over 2. So that works well with that. It's a multiple of it. Pi over 2, the phase shift is a multiple of the scale. If you're not sure, if you're like, well, what do you mean it's going to work well? You watch. I can look at that and see that pi over 4 is going to count out to pi over 2. Well, I've got everything I need. I haven't forgot about the vertical reflection, though. A scale. It's got to go up to amplitude 4. So 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4. Listen, folks, I encourage you, print out or get some graph paper to do these. If you try and do these on regular lined paper and just try to draw them on there, you'll get the points all messed up. Things will just get all messed up when you try and do that. So get yourself some graph paper to do these on. Okay, and the period was pi, but the scale's pi over 4s. So again, I'm going to do this thing where I go pi over 4, 2 pi over 4, which is pi over 2, 3 pi over 4, and then pi. Wait a minute. Oh. It said domain 0 to pi. That's not going to work. I got to get rid of all that. That's no good. I got to do the domain they wanted. So then I'm still going to use pi over 4 as a scale, but I'm not going to do that thing where I do every second square this time. Pi over 2, 3 pi over 4. I'm just counting by pi over 4s here. 4 pi over 4, that would be pi. 5 pi over 4. 6 pi over 4, which would be 3 pi over 2. 7 pi over 4. And then finally 8 pi over 4, which would be 2 pi. See, now I've got that 0 to 2 pi. Confused by that? Well, you can write them out at the bottom here and just go, okay, I'm just counting by pi over 4s here. And all I did along the way is reduce the ones that would reduce. So when you're first doing them, if you need to write that scale along the bottom to help yourself out, that's fine. Okay, so my first graph that I'm going to do is going to have the right amplitude and period, but I'm going to use the vertical reflection in there too. And I'm using this light orange color. Maybe you'd like just to do it light pencil. Okay, so this is a sine graph. So it starts at 0. And on the key points, it first goes up normally, doesn't it? Sine normally goes up to its top immediately after that. But with a vertical reflection, instead, it's going to go to its bottom. So that's where I'm using the vertical reflection, is on my choice of where the key points go to, because sine normally will immediately go up to its top point. I'm going to immediately go to the bottom. Then middle, then the top, then the bottom. By using a scale of 1/4 of the period, I've exactly drawn one cycle in the right period, which was pi here. That is not, so I've got the negative in there, I got the 4, I got the 2, I've got all that stuff in there. That's not the proper graph. So that's why I don't connect the dots up. I'm just using those as reference, because I got to take all those and move them right pi over 2. And here's what I was talking about the scale being compatible with the phase shift. Pi over 2 is 2 squares. And so moving exactly 2 squares is nice, because that scale has worked out very well with the phase shift. So I got to take each of these and move them right 2 squares. So right 2 squares, right 2 squares, right 2 squares, right 2 squares, right 2 squares. There's my graph. The red points. They weirdly have gone through some of the yellow points. It said graph it from 0 to 2 pi. So I've got to continue this pattern. The next point would be there and there. Just following the pattern to get extra points here to get from 0 to 2 pi. These next points would be there and there. Sketch the graph 0 to 2 pi. I sketched it 0 to 2 pi. I didn't put arrows on it because it said just go from 0 to 2 pi. Well, that example had a little bit of everything in it. So that one is the one that you should go back to when you're having trouble, because that one covers all the little pieces of this situation, except for one little thing. But this one little thing is something you've seen before. Example 7. Take a look. This graph is not ready to be completed yet. I'm going to actually write in black because I'm going to have to do something first. You've seen this before. The x has to be by itself for transformation, so I got to common factor out that 1/2. So what I actually end up with is x plus pi. When you factor 1/2 out of pi over 2, you get a pi. There's the graph I got to use. So that's the only extra thing that I have to do in this question, is watch for that common factor inside. The rest of these steps will be exactly the same as the last one I just did. They want from negative 4 pi to 4 pi, so I got to watch out for that in the middle of all this. But here come all those steps one more time. Amplitude, 3. Period, 2 pi over the k value. The k value is 1/2. Isn't that weird? I'm going to write it like this. 2 pi divided by 1/2, which is 2 pi times 2 over 1. So the period's 4 pi this time. That was a horizontal stretch by factor 2. It made the period bigger. Oh, that's going to work pretty well, though, with that domain they want there, so that's okay. What was next? Phase shift. Pi left. See, it wasn't, it was tempting to say that it was pi over 2, but it wasn't. It had to be common factored first. So it's pi left that this thing moves. And then vertical translation down 1. The final piece of the puzzle is what scale to use. And I always put scale question mark there to remind myself that I better check the phase shift when I'm done. And the scale I'm going to suggest that's going to work very nicely every time is take the period and divide it by 4. Here the period was 4 pi. Dividing that by 4. A nice scale of pi should work well. Check it with the phase shift. It's going to work nice. This is a nice one. The phase shift is pi. I'm suggesting a scale of pi. That's going to work very nicely. They want, I'm going to again skip some squares here just to make this work out real nice. They want this graph to go this way too, though. Okay. And I'm ready with my orange, my light orange that I'm using on here. For you, I suggest just draw your points very lightly with your pencil. I've seen people do it in pencil and pen. That's a little bit dangerous, so you happen to make a mistake, but it does really have the effect of what I'm doing here, is that the original points are in nice light pencil, and then you go over top with a pen or something like that. Okay, cosine starts at the top. And the top for this graph is at 3. Then, at pi, we're back to middle. 2 pi, down to the bottom. Middle, top. See? By using period divided by 4 as my scale, after I do 4 points, I get exactly a whole period of the graph. Perfect, one whole cycle. But these points need to be moved, and now I'm going to switch to my crazy red. Each of those points needs to be moved pi left and down 1. Pi left is exactly 2 squares, so pi left and down 1. There's that first point there. Pi left and down 1. Pi left and down 1. Ooh, that almost didn't fit on my graph there. Pi left and down 1. Pi left and down 1. And so now I can draw a full cycle. But they want from negative 4 pi to 4 pi, so I just got to continue the pattern and get some more points. So there, and there, and then there, and then there. I just sort of looked at how many squares I had to go left, right, and up, down to get the next points. And so I'm going to label this graph y equals 3 cosine. I mean, I've used my version of it, x plus pi with the common factor in there. Ooh, did I remember to label this graph up here? Ooh, I don't think I did. Oh, let me just put that on there. Equals negative 4 sine 2x minus pi over 2. Okay, back to my example. Okay, so nice title on there. You can double check these graphs. If you're having trouble with them, you can double check them with something like Desmos and just type the graph right in to make sure that you're getting right answers and so on. Because sometimes the back of the book, they show a picture of it and the picture's hard to read or hard to follow. I really suggest in this section you really go to the solutions or go to Desmos. It's a great app, free app. But there's also a website, and it's great for graphing these things and comparing your answers to make sure you got things right. Okay, lots of graphing. Make sure you get really familiar with all these steps. It will come faster as you go along. So if the first few questions take you forever as you work your way through this, that's sort of natural, and you'll just get faster and faster.